Good evening and welcome to Monday Night Calculus. My name is Curtis Brown and I am joined once again by Steve Kokoska and Tom Dick. I am super excited that you guys are here joining us this evening. We will be talking about polar equations tonight, and Steve and Tom have some great things prepared for you all, ready to go. And so, Steve, I will let you take it away.
All righty. Thank you very much, Curtis. I'm going to share my screen here. I'll see if all of this works. Hope you can see that. And I'm going to make this a little bit bigger if I can. How's that?
Okay. Looks good. Looks great.
Indeed, we're going to talk about polar equations tonight, Curtis, but actually calculus with some polar equations. And thanks for handling all of the technical issues tonight. And Tom, it's always good to see you out there on the left coast. I enjoy this a lot. This is one of my favorite topics, Curtis, because one of the reasons is because we can produce lots of absolutely beautiful graphs associated with functions, expressions in polar coordinates. And Tom's going to show you some of the technology in a little bit. It's a huge help with this topic. So here's what I'm going to talk about tonight, start with anyway. I'm going to give you a little bit of background as usual, and then I'm going to solve some problems here. So let's consider a polar curve described by r equal f of theta. And I'm going to assume, especially the BC students out there, that you're familiar with this type of equation, r equal f of theta, that you're familiar with, say, plotting some of these by hand, and maybe even using technology to help you along the way. So we usually let theta be the parameter that we use here, and we write parametric equations. We can write some parametric equations to describe the curve like this. And we also use these equations, remember, to go back and forth between polar coordinates and rectangular coordinates. So these two equations I can think of as parametric equations. As Tom will probably show you, this is kind of a sneaky way to draw a polar curve if you wanted to do it this way. And one of the very first things I'm going to talk about is finding the slope of the curve at a specific point, a polar curve. And to do that, I'm going to go back to my definition of parametric equations, or the slope of the parametric curve. And remember, that's dy dt divided by dx dt, but my parameter here is theta. So the slope along the polar curve at any point would be dy d theta divided by dx d theta. Now, where did these two ugly looking equations come from? Well, I know what x is. Let's see, I'll take a look at the denominator first. I know what x is. R, we write the expression for r as f of theta, and really, that's just a product. And so all I did was use the product rule twice to get that expression in the numerator and the denominator. Now, one of the things that we often see, or one of the questions we often see in an AP Calculus exam is, well, find the places on this curve where there is a horizontal tangent line, or find the places where there's a vertical tangent line. Well, just to remind you, we'd have a horizontal tangent line if we look at this expression right here, where the numerator is 0, dy d theta is 0, provided that the denominator is non-zero. And we have a vertical tangent line where the denominator is 0, provided that the numerator is not equal to 0. So Curtis, here's one question that we can throw out right away here. What do you do if you find a value of theta that returns both dy d theta and dx d theta equal to 0? And I'll kind of leave that as an open question for a minute.
So what do we do if I get dy d theta equals 0 and dx d theta equals 0?
Right, for the exact same value of theta. What do you do? How do you figure out the slope of the tangent line? What do you do in that case? Okay.
I think that sounds like an interesting question.
There's a lot of good calculus ideas coming here.
That sure
I'm going to
is.
answer that one. Okay.
I'm not going to answer that one. I'm going to let the audience tackle that one tonight.
Okay. And this is just kind of an extra result here. You know, sometimes we have to find a tangent line to a polar curve at the pole, and at the pole, r is equal to 0. So all I did really was take this value of r equal to 0 and plug it in up here. And if you do that, these two terms drop out. And let's see, I have dr d theta divided by r d theta. Those cancel, and I end up with the tangent of theta. Again, provided that dr d theta is non-zero and that the cosine of theta is non-zero. So that's a lot of background there, mostly associated with finding the slope at a particular point along a polar curve. So let's take some of this information, take some of these results if we can here, and try a couple. So this one's going to be a hard exam, and let's consider the graph of the cardioid described by r equal 1 minus cosine theta. And for the AP Calculus teachers out there and the students, I know your students are better at this than I am. They can recognize some of these curves right away and know that that's a cardioid and kind of know where the larger portion of the cardioid is in which direction. So I want to find the slope of the tangent line to that graph when theta is equal to pi over 6. And I want to find the points on this cardioid where the tangent line is horizontal or vertical. All right, so here we go. I got to find dy dx. So what I did is I went back to that expression on the previous page. So up here in the numerator, I have dy d theta, yes?
I do have one question. I'm going to interrupt you while you're talking.
Sure, please.
Alejandro is asking if we are going to go over anything with polar arc lengths tonight.
I do actually have a question, I think, about arc length in here.
In the assignments or in the presentation?
No, I think I have one in my presentation.
Well, fantastic.
I do. I beg your pardon. I think it's, oh, wait a minute. I don't know. Wait a minute. Hang on. I know I've got one somewhere. I know.
Okay.
I think it's in the assignment.
Okay.
Okay.
Well, I will, I'm going to post a link to that here in just a second anyway. So,
okay. All right, so up in the numerator, I've got dy d theta. In the denominator, I've got dx d theta, and I multiplied through, and I'm doing a little bit of simplifying. Now, what I did from this step to this step looks a little funny here, but what I'm trying to do is to get everything in terms of either all sines or all cosines. And what I did is I simply used the trig identity to replace sine squared with 1 minus cosine squared. I made a decision here to get everything in terms of cosine up there in the numerator. And I didn't do that in the denominator because once I made this switch here, once I made that substitution, I noticed that I could factor the numerator, and I can do a little bit of factoring in the denominator without any other sort of trig identity. Now, I did that because I'm kind of looking ahead a little bit here. I know that I'm going to have to find places where the numerator is 0, find values of theta where the denominator is 0. And so that's a lot easier, or the standard technique here is to factor completely the numerator and the denominator to do that. All right, so I'll get there. Here's an expression for dy dx. Here's an expression for the slope on the polar curve at a specific value of theta. So the first question simply asks, well, what's the slope of the tangent line when theta is equal to pi over 6? So, okay, there's a lot of work on this page. It's kind of big here. But I simply substituted in theta equal to pi over 6. Let's see, I've got the cosine of pi over 6 here is square root of 3 over 2. Oops, sorry about that one. Got the sine of pi over 6 is a half. And I did a lot of simplifying here. I hope I didn't make a mistake there. And son of a gun, that turns out that the slope of the tangent line to the polar curve at the point where theta is equal to pi over 6 is 1. How about that? And because I like to visualize this stuff, and because Tom will probably show you some of this, here's a graph of this polar equation and the tangent line. There's the cardioid. You can see why we think of this as kind of a heart shape. It's kind of tilted on its side. And there's the tangent line. And here's just another question. Here's an easy one to get people going. Well, I know that theta was equal to pi over 6. Where the heck did that 1 minus the square root of 3 over 2 come from? That's actually the x and the y, pardon me, those are the polar coordinates for that point. But where'd the 1 minus square root of 3 over 2 come from, I wonder? Okay. Let's try B. Well, in order to find the horizontal or the vertical tangent lines, I've got to find places where dy d theta is equal to 0 or pardon me, where dx d theta is equal to 0. So let's see if I've got this right. You can see now why I've factored both the numerator and the denominator. So I'm looking at the numerator first, where dy d theta is equal to 0. And I call this the principle of zero products. And to me, what that means is if I have a product equal to 0, the only way that that can happen is if one of the factors is 0. And we use this all the time. We use this principle, I think, all the time in mathematics and calculus. So, okay, a little bit of this is kind of slurred together here, but here's one term. I set that equal to 0. I solved for the cosine of theta, and I thought about, well, okay, where is the cosine of theta equal to minus 1/2? I've got a 2 pi over 3 and a 4 pi over 3. Now, I'm only looking at values of theta between 0 and 2 pi. I snuck a little something by you. I know that I get a complete curve. I get that complete polar curve when I go 0 to 2 pi. So I set this expression equal to 0. That means I have to find values of theta where the cosine of theta is equal to 1, and that gives me a 0. Now, I'm not convinced yet that all of those values of theta do indeed lead to horizontal tangents. I'm going to hold that solution, hold those three values aside for just a second. I'm going to take the denominator and I'm going to set it equal to 0. And once again, the principle of zero products. So where is the sine of theta equal to 0? Well, it's 0 and pi. Where's the cosine of theta equal to 1/2 pi over 3 and 5 pi over 3? So let's see if I can kind of summarize what I've got now. I know where the numerator in that expression is equal to 0. I know where the denominator in that expression for the slope is equal to 0. So I know at these two values right here, I know by looking at these four, I know that the denominator is non-zero. So that means I definitely have horizontal tangent lines at those two values of theta. I know for these three values, I know that the numerator is non-zero. So I know I've got vertical tangent lines at those three values of theta. But now I've got this one issue here where theta is equal to 0. I get both a 0 in the numerator and the denominator. Did anyone answer this one yet, Curtis, about what we're going to do?
Well, not so much about what we're going to do, except for what we might be able to expect. Alejandro mentions that he believes there's a cusp or a short turn at that value. That's kind of his hypothetical. He also asks another question about whether we're going to convert. I think this is related to your previous question about whether we're going to be doing any conversion between rectangular and polar coordinates tonight.
You know, I'm actually not going to do any of that.
I didn't think so.
Yeah, that's kind of as a preliminary to this, I think, to this presentation. Okay. So what do we do with that 0 over 0? We'll get there. So I know I've got horizontal tangents at these two places where theta is equal to 2 pi over 3 and 4 pi over 3. I know I've got vertical tangents at those three values of r theta. However, at x equals 0, we have both dy d theta and dx d theta equals 0. And so what we need to do is we need to take a look at a limit. We need to see what's happening to that expression dy dx as theta goes to 0. Now, I apologize, Curtis, I didn't put any reasons off to the right-hand side, but maybe you can help me a little bit. I actually made one step here. I took a limit as theta goes to 0 of that large expression dy dx, and I split it up into two separate limits. And I can do that because that's one of the properties of limits, so long as these two separate limits exist. Well, let me follow this a little bit further. Let's see, I claim that this first limit here is equal to -3. Anybody tell me why that's true? How do you know that? How do you know that first limit right there is -3? I see the minus sign out in front. Okay, but where'd the 3 come from? How do you get that? And maybe
I'm
more.
going to watch and see. I'm going to see somebody respond to that.
Okay.
While we're waiting for that, I do see Mark Crowley asks, "Does the 0/0 involve a limit?" And I think we've got that answer.
Absolutely, Mark. Very good.
It's definitely got that
Yep.
for there.
All right. Well,
so we'll kind of watch and see. Steve, go ahead.
All right.
We'll kind of see why folks maybe have this 3 coming in.
This is good review, I think, Curtis, too, as we're coming up on the AP Calculus exam. It's good to think about how do we solve. There's a lot of different ideas, I think, that come into play here in solving some of these problems. So why do you, or how and why do you get that 3? Where does that come from? And what about this other one over here? How do we figure that limit out? Well, one of the things I guess I teach my students is you might try direct substitution. And what happens if you let theta equal to 0 in that expression? Can you see quickly what happens there? If I let theta equal 0 in this second limit, anybody see what happens?
Yeah.
Was that a yes or no, Curtis?
That just seems to me like I mean, I don't know. I'm going to make myself look silly, but it seems like it approaches 0.
Almost.
Right?
Well, as theta goes to 0, what's the numerator doing? The numerator is going to the cosine of 0 minus 1, which would be 1 minus 1 or 0.
Yeah.
What's the denominator doing?
Well, it's approaching 0.
0 also.
Mm-hmm.
Now you'll notice I didn't write an equal sign in there, okay?
Mm-mm.
Boy, how did I get all the way down there? I didn't write an equal sign in there. Sorry about that, Curtis. I don't know what happened there.
That's all right.
Here we go. You notice that I didn't write an equal sign, and that's one of the things we'll talk about on our last Monday Night Calculus is some tips for the exam. Remember that if you see an expression, a limit expression that is 0/0, you don't want to equate that to 0/0. You should.
Right, but it approaches it. Yeah.
Technically, the right way to do this for the exam would be to come off to the side here and say the limit as theta goes to 0 of the numerator is equal to 0. The limit as theta goes to 0 of the denominator is equal to 0. And therefore, this is in an indeterminate form of type 0/0. And son of a gun, I need to use L'Hopital's rule here. So that comes in.
Hey, I just got that from Tammy Brown. Just posted that in the chat. Said, hey, beautiful. we need L'Hopital's.
Very good. Excellent. So I took the derivative of the numerator, the derivative of the denominator, and once I did that, well, now I can try direct substitution. I get a 0 up here in the numerator. I get a 1 down there in the denominator. So that whole fraction is approaching 0, which means the product is approaching -3 times 0, or just 0. So what does that mean? Darn it, the slope of the polar curve as theta goes to 0 is approaching 0. So indeed, the graph has a horizontal tangent line at the pole. That's a cool problem. Let's put all of this together here. Here's a graph, I think, of all of these results. So there's my cardioid. Let's see, we had 2 horizontal tangent lines right there and right there with theta equal to 2 pi over 3 and theta equal to 4 pi over 3. Here are the 3 vertical tangents that we found. And then finally, it's kind of hard to see, but there is a green segment in there. There's the other horizontal tangent. And in fact, somebody mentioned already, there's kind of a sharp corner or a cusp there. And that is correct. It's kind of cool. All right, let's take a look at another idea here. Let's consider some areas of polar regions. So I'm not going to derive this, but let's let R be a region bounded by the graph of a polar equation, R equal f of theta. And here's my picture of all of this. And by the rays, theta equal A and theta equal B. And let's assume that f is a positive continuous function for 0 less than b minus a less than 2 pi. Now, again, I'm not going to derive this, but this is really a cool, I think, method or result for you to do in class, because it's another very good example where we make an approximation and we get better and better approximations, and we let n go to infinity and we discover a calculus concept with another Riemann sum. And so my picture is going to get a little messy here, Curtis, but what we do, of course, is we break this region up into small rays like this, and we can find actually the area of that sector of a circle. And we take all those areas and we add them all up and we get an approximation to this shaded blue area. And then we take finer and finer or more and more divisions in there. We let n go to infinity and we discover this calculus concept, where the area of that region R is the integral from a to b of 1/2 r squared. It doesn't matter to me, and the truth is it doesn't really matter to us when we're grading the exam where that 1/2 appears as part of the integrand or outside the integral. Doesn't matter so long as that constant is there. So let's see if we can apply this. Let's see if we can find the area enclosed by one loop in this 3-leaved rows. How about that? Described by r equal to cosine of 3 theta. So I've taken the liberty here of sketching this curve, and I actually know a little bit about how, let's say, a particle or how this curve is traced out. And I know that if I started with theta equal to -pi/6, I would start here at the origin, and then as theta increases through 0 and pi/6, I move around this curve and I get one of those loops. So I've got to find the area of one of those loops. And to me here, as we do this, I think this is just really cool. So I'm going to make a lot of nice things coming into play here again, Curtis. I'm going to use some quick tricks here, I think. I know that the area of that region is bluntly straightforward here, 1/2. The integral from -pi/6 to pi/6, and this is just my r in here squared. Now, I can see from that graph that there's a lot of symmetry in here. So what I'm going to do is multiply by 2 and go from 0 to pi/6. And I'm going to do that because I know there's some symmetry there, and I have this feeling that it will make it a little bit easier for me to do the evaluation once I've got an antiderivative. Okay, so the 2 and the 1/2 cancel. There's a constant 1 out in front now. And I found an antiderivative. Here's another question here. Oh, I'm going to find an antiderivative eventually here. How do I go from this step down here to that step? This is kind of a common, not trick here, but common method here to integrate a trigonometric integral that involves, say, a sine squared or a cosine squared of an angle. And there's a missing d theta there. Sorry about that. So we'll leave that question out there. How do you do that? How did I get that? What sort of, not trick, I hate using that word, but what sort of method did I use to rewrite the cosine squared of 3 theta as that expression? Now, once I've got that, I brought the 1/2 out in front, and now I just integrate term by term. And the integral of 1, of course, is theta. And okay, there's a very easy substitution going on here, but I know we're all good at this. We're late into the course, and you can all see that just by looking at it. It's 1/6 times the sine of 6 theta. And let's see, I plug in the lower bound. I know I get a 0. That's pretty easy. I plug in the upper bound, and let's see what happens here. I got a pi/6, 1/6 sine of pi. Well, that's a 0. And so I'm left with just pi/12. Kind of looked a lot bigger on the screen there when I graphed that. But the area of one loop is exactly pi/12. Any answers to this one, Curtis? Where'd that come from?
So I got the power reducing identity from one of our folks out there.
Power reducing identity. Okay, so there are certainly some reduction formulas. And that's a very, you could actually use, I think, a reduction formula here. But I think this one, there's another way to do this even easier, using a trig identity.
I was going to say, the trig identity kind of was floating in my mind there, right?
Yep, a half angle formula.
Half angle identity, yeah.
Yep, and that's a common trick, common method. All right, let's try one more here. All right, let's see if we can find the area.
Yeah, we got a couple of more folks now stating the half angle identity.
Good, very good. All right.
So,
Let's see if we can find the area of the region that lies inside the circle described by r equal 3 cosine theta, and outside of the cardioid, here's another cardioid, described by r equal 1 plus cosine theta. So once again, I've taken the liberty here of drawing both of these polar curves, and I've shaded in the region. So I got to find the area of this blue shaded region. And I'm going to show you this on the next page, but I know I found that these two curves intersect when theta is equal to pi over 3 and when theta is equal to 5 pi over 3. So the way that we're going to actually find the area of the shaded region is a technique that we use in just rectangular coordinates. Think of rectangular coordinates in an upper curve or a high curve and a low curve. We found the area underneath the high curve, we find the area underneath the low curve, and we subtract to get the area that we want. And that's exactly what we're going to do here. Now, this may look a little complicated at some point here, but it's not that bad. First thing I'm going to do is I'm going to solve that equation and verify for you that those two curves do indeed intersect at pi over 3 and 5 pi over 3. Now, again, in these polar problems, there's often a lot of symmetry. And rather than go from pi over 3 to 5 pi over 3, or pardon me, I'd actually have to go from 5 pi over 3 to pi over 3, I'm going to do it this way. I'm going to go minus pi over 3 to pi over 3. I'm going to sneak back up here to this picture. So this point right here, I can also reach with theta equal to minus pi over 3. So when I do that and I recognize a symmetry, oops, sorry here, Curtis, here's r squared for the outer curve for the circle. Here's r squared, maybe I should call that r sub I and r sub O for outer and inner. There's r sub I squared. And again, I know there's an awful lot of symmetry here. So for both of those expressions, I'm now going to go from 0 to pi over 3. And I'm going to put a 2 way out in front. And of course, the 2 and the 1/2 will cancel. This still looks like a bear. Let's see what happens here. All right, so here's what I did. I took this expression here, factored out the 1/2, cancel with the 2. And then what I tried to do is to combine everything into one definite integral. And let's see, did I do that right? I'd have a 9 cosine squared minus 1 cosine squared. Yep, I see that. There's the 8 cosine squared. I see the minus 1. And I see the minus 2 cosine theta. Got that. Okay, holy Toledo. How do I integrate this? Well, let's see. This one's easy to integrate. I can find an antiderivative of 1 pretty easily. This one's pretty easy to do. I know an antiderivative of the cosine. And this one right here, cosine squared, is actually a fuzzy easier than the one that we just did where the argument was 3 theta. So once again, I'm going to use a half-angle formula.
So Steve,
yep, go ahead.
I just got a question on the chat about they didn't think the exam would use a problem that required a power reducing formula. But I think if we're talking about these, half angle identities, I think that's fair game, right?
I think knowing the trigonometric identities is fair game, and I'd even go so far as to, it's quite possible that in the statement of a problem like this, they might even remind you, hey, don't forget about this identity, or don't forget about these 2 identities. You may need these. That's in the spirit of these problems when they give you a volume of a cone or something like that, and they'll give you the expression. But I think this is fair game. Yeah, Curtis.
Okay, I was just verifying that. And I would be remiss if I didn't call out that Virginia nailed the half angle identity earlier as well.
Good.
Needed to make sure that I called that out.
All right, so here's what I did. I multiplied through that 8.
Steve, I'm sorry to interrupt you, but it's on that same topic. Another possibility is a problem like this might very well appear on the calculator open part of the exam.
Ah.
In which case, you wouldn't even be expected to find an antiderivative. You would just be expected to evaluate the definite integral using the calculator. So, because all the calculus would be in getting that set up.
Yep.
Sure. Right.
Yep. So you would be expected to set it up, and then we'd be looking for an answer with 3 digits to the right of the decimal. Yep. Absolutely. Well, still being old school, I think there's some value in doing some of this. So I multiplied out, collected some terms, pretty straightforward antiderivative, plugged in the upper bound and the lower bound, and son of a gun, the area of that region is exactly pi. That to me is absolutely amazing, that we can find the exact area of that region. That is really something. All right, I'm going to take a quick look, Curtis, if it's okay, at some of the solutions here from these exercises. I hope people handed in their homework. This is kind of a neat problem. This one we call spiraling under control. And we're going to consider a curve that's r equal to 2 theta divided by pi. And I'm going to rewrite this just a little bit. I'm going to write this as 2 pi times theta. Because before I even look at a graph of this, I kind of just want to think about that equation. You know, it's good if we can sort of reason out what that graph might look like. You know, there's a constant out in front times theta. So this is kind of saying in words that as theta increases, the distance from the origin is getting bigger, is increasing. And if you just think about that and say that a couple of times, you kind of get the idea that we have this spiral, but it's increasing in distance away from the origin. So I want to sketch the curve, and I want to find an equation of the tangent line to the curve with theta is equal to 3 pi over 4. Here's a nice sketch of the curve right here. And for theta equal to 3 pi over 4, one of the first things I did is maybe this will appeal to Alejandro a little bit. I did convert here from polar to rectangular. I found the x and the y coordinates. Here's the x coordinate, there's the y coordinate. And this is kind of ugly here, but here's the slope of the tangent line. This is using the 2 formulas that we talked about at the top of the show. And I need to plug in a theta equal to 3 pi over 4, common angle. So I know the sine and the cosine there. I found the slope of the tangent line. And boy, that's an ugly looking tangent line, but there it is. And there's my graph up there. So I feel pretty good that I found the right slope, that I've got the right equation of the tangent line. That's kind of cool. Now I'm not done with this one. I want to find the first value in the interval between 0 and 2 pi where the tangent line to the curve is vertical. We're going to think back a little bit here. How do I do that? I've got to find the first place then where dx d theta is equal to 0. Okay. So I found dx d theta. I'm going to set it equal to 0, and try as you might, I don't think you can factor that in any way. I don't think I can find a nice analytic or symbolic solution there. So I actually went to my calculator and found theta equal to 0.8603. And I double checked just to make sure that the numerator was non-zero there, and indeed it is. And so the first value of theta, where we have a vertical tangent line, is theta equal to 0.860. I'm just going to scribble a little bit here, Curtis, because I saw this come up on the AP Calculus Facebook page. The answer here, let's suppose we actually asked the student for this answer for this value of theta, and it was on the free response portion of the exam. And the question was, can a student just respond with 0.86 because the third place there is a 0? And the answer is yes. You can just write 0.86 without the 0 there. It's not necessary. Okay, that's correct to 3 decimal places.
Good.
All right, and let's see if we can find the area of that region R bounded by the curve and this line segment here from the origin out to 4. Well, we know how to do that. We've got a formula for that. And this works out really cool. Here's 1/2, 0 to 2 pi. I actually have to go sweep out all of that area as theta goes from 0 to 2 pi. Here's my value of R. instead of I've got a lot of constants out in front here, and this integrand just becomes theta squared. Boy, that's a pretty easy one. Theta cubed over 3. And I think when I plugged in the upper bound here, and then 0, and simplify, I get a 16 pi over 3. Cool.
That's a cool problem.
And here's one. Okay, I thought we had one here on the exercises. How do we find the length of that curve? Well, I have a good question here. I have a good question in this one too, I think, Curtis.
All right.
How do you find the length of the curve C? Well, we go back to the formula for the length of a curve, and I'd have to go 0 to 2 pi. How does the parameter vary? Goes from 0 to 2 pi. It's a square root of dx d theta squared plus dy d theta squared. Now, I've got a lot of dots in here. Dx d theta, dy d theta are kind of complicated. And then I've got to square them all out, and I've got to simplify. And believe it or not, if you do all of that, you're left with, in the integrand here, it's just a square root of 1 plus theta squared. Now, the question is, how the devil do you integrate that? Now, I've got a kind of a funny looking answer here. It looks kind of complicated. This is not an easy, simple U substitution, because I don't have the derivative of that inner function as part of the product, as part of the integrand. And so it's not a simple U substitution. It's not integration by parts. And so how do you do that one? You don't everybody doesn't cover this, I don't think, even in a BC calculus course. That's why something like this would probably be calculator active question.
Magical ellipses, I think, is the
magical ellipses. I don't know about that one.
That's one of the responses I've gotten in the chat here. Is magical ellipses. I like those dots that
like
kind
that.
of, you know.
Yes, there's a lot going on in there. Well, I think Tom will have to back me up on this one, but I think in order to solve that, if you wanted to do it analytically, I think you'd have to actually use trig substitution in order to do that. So
yeah, I think right. Also, I think the point would be made again that with an integrand this complicated, a question like this is, I think, fair game, but it would appear on most likely on a calculator open part of the exam. So you'd have the capability of finding a definite interval just numerically.
Yeah.
Absolutely. Yep. All right, I'm going to take a look at one more kind of quickly here, Curtis, and then I'll pass it over to Tom. Let's take a look at this rabbit ears graph. Perfect, just after Easter. How about that? Consider the curve C defined by this polar equation, 12 sine theta cosine squared theta. I've sketched this curve, and we want to find the polar coordinates of the point on the curve in the first quadrant that's farthest from the origin. Now, I've done an awful lot in this first step. There's an awful lot going on behind the scenes. But what in fact is the distance from any point on this curve to the pole? It's actually the value of r. And so what I'm really trying to do here is to maximize that expression for r. And so how do you do that? Let's think of this as a calculator active problem. I have to take the derivative of r with respect to theta, and I have to set it equal to 0 and solve for theta. And in fact, I did. And I used a graphical analysis here, and I'm not going to go through all of that, but I did see that dr d theta changes sign from positive to negative at this value of theta. And as you can probably almost guess here by looking at the graph, you can almost guess that the point where farthest from the pole, farthest from the origin, is about out there, sort of at the midpoint of that ear on this graph. And here are the polar coordinates I found using my calculator. If we wanted to find an equation of the line tangent to the curve C at that point, we can do that. This is all numerical. I've drawn, again, the curve and the tangent line in there. And I think I have one more part of this. find the total area enclosed by that curve C. Well, I happen to know that I get this loop here as I go from 0 to pi over 2. I'm going to double that because of the symmetry. And this expression right here is r squared. Okay, so how do you integrate this if you really wanted to do it by hand? This is where you'd have to use these reduction formulas, or what I would call reduction formulas, to reduce the powers on those cosines. So I did all of that. There's an awful lot going on. I guess, what did you call those? Magical ellipses?
Magical ellipses.
I like that. Okay.
That's Mark Corrali on that. I'll give him credit.
And I ended up with a 9 pi over 2.
I always said it can be shown that.
That's good. I like that. All right. Well, thank you, Curtis.
Shorthand for a miracle occurs.
A miracle occurred.
All right. I'm going to try a miracle here, Tom. I'm going to stop sharing and turn it over to you. There we go.
Uh-oh, Tom, you're going to have to unmute yourself here. Somehow you've gotten yourself muted again.
Sorry about that. Okay.
There we go.
I'm actually going to try to share TI-84 screen, if I can. Let's see if this works. You guys can give me some feedback in case it...
I'm seeing Nspire right now, Tom. Oh, there we go.
Okay, does it look like the TI-84?
It sure does.
Okay, great. Okay, thanks. So the curve that we are looking at here is, I think it was 5 times the square root of cosine 2 theta. Can you, is that right, Steve?
Yep.
Okay. So I just wanted to show, I think graphing calculators is really revolutionized the way we can talk about polar curves in the classroom. The chance of actually being able to graph these more easily, so we can talk about their interesting properties, is so cool. So if I just go to my regular y equals menu, of course, the normal thing we see is the setup for plotting functions. So it's the y1, y2 equals. So if we want to go into a polar plot, we're going to want to go over here and change the mode. And there's lots of different modes here for like numerical display, angle measure, and so forth. I want to go down to this 4th line where it has function. That's what we're normally in. And then I'm going to arrow over to polar and enter that. Okay, now if I return to the y equals screen, the y equals is really kind of a shorthand for whatever kind of function you're dealing with. In this case, it's a polar function. And now notice what we've got here. We've got R1, R2, and so forth. And our variable, independent variable here is going to be theta. So I'm going to go ahead and use this curve we were talking about. I think it was 5 times the square root of the cosine of 2 times theta. And you might think, well, I've got to search around for a theta key or find that in some kind of menu. But actually, this key that has x comma t comma theta, it's sensitive to the mode that you're in. And so if we're in polar mode, that's a theta key. And so we get a nice theta symbol there. And I think we are good to go there. And now I'm ready to graph. I'm just going to use a zoom decimal window. That's where I have equal scaling in both the x and y. And let's see what kind of figure we get here. Ah, interesting. Okay, it looks like we've got some missing parts here. So we might wonder what's going on here. You notice the title on that was an infinity curve, in quotes. And so you might have been expecting, we're going to see something that looks like a figure 8 on its side. Well, let me go to the Windows settings and see what we've got there. Well, we've got, notice this looks different too. We've got theta min, theta max. It's referring again to our independent variable theta for polar curves. So 0 to 2 pi, I wonder if we need to change that to a larger value. And Curtis, feel free to chime in if you have any insights here.
I'll chime in momentarily.
Okay. I'm going to change it to 3 pi for my domain. And let's see, we do have a pi symbol here. And it will actually calculate that out. There we go. And let's go ahead and graph again. So there's these missing parts here that are kind of curious. So we might wonder what's happening there. Okay. So I've got another thing I'm going to try here. I'm going to go back to my window. I'm going to change that theta step size and make that actually smaller. Okay. In fact, I'll make it.
So Verge is suggesting that we need to go all the way to 4 pi to make that make sense. Can you show me the equation again really quick just to verify that I'm doing the right thing here?
Yeah, here we go. 5
cosine of 2 theta. Okay. Yeah, I think 4 pi makes a little bit interesting.
Great.
And I've got another question that came in from Renee Williams. We're interested here in the difference between zoom decimal and zoom square and why you might want to use each. Square gives you just a direct, and Tom, go ahead and respond to that too as I get done with my response. Square gives you just a purely square window, right? So we get equivalent distances such that we have a square looking grid on our screen. So if I showed the grid, I would get squares. So it becomes a proportion to the ratio of the screen, because that screen is not square, right? So if I set it, if I say zoom square, I get squares on my screen. However, zoom decimal sets me up so that I can have integer values or nice looking values as I scroll across the screen.
So it is true that a zoom decimal window will be square.
Right.
In the sense that each pixel will be worth actually 0.1 in both directions.
Right.
And so it is an example of a square window. I think the zoom square also, it kind of deals with whatever your x min, x max is.
Right. Right.
It
squares the window for your current x min and max.
Right.
Mm-hmm.
Yeah. Okay.
Tom, am I correct with zoom square? The way that I've always thought about this, doesn't that make a circle look like a circle?
Right.
Yes,
right?
Exactly. Yeah, it squares up.
That's exactly what it does. And so what it sets it up so that the ratio of pixels on your screen actually, because the zoom standard is -10 in both directions, -10 to +10 in both directions. But if I hit zoom square, it actually chops off the vertical axes to make sure that I end up with circles looking like circles and things of that nature, right? So units in the horizontal direction are the same pixel size as units in the vertical direction. Does that make sense? Did that help answer your question, Renee? I hope it did. Try -4 pi to 4 pi, Tom, just to make sure.
Closer, Tom.
We're good here. I apologize for not helping you there.
Okay. All right. So you're thinking maybe -4 pi.
Yes. 4 pi to 4 pi. And while you're at it, do pi over 24 for your step.
Well, I actually have pi over 96.
Oh, okay. Okay. Well, that'll give you, that's sufficient.
Oh, it didn't like this. Let me see what I did wrong. Oh, I think I used probably the negative or
There
the
you
subtraction sign instead of negative. Okay, that's a common glitch there. Okay, there we go.
Getting closer. We got one more who suggests negative 8 pi to negative 8 pi to 8 pi. Tom.
All right, let's try one more. Yeah, this has been fun.
So this is one of these interesting things that can happen, right? You've
yeah, and I'm
got
not
your
bothered
problem
by this
set
at
up,
all
and
because this is one of the things we want to talk about is working with the calculator, and so I'll try
making sure that your window gives you. Nope, you don't want 8 pi as your step.
I skipped down one too many. Let me go ahead. I'll go ahead and make it pi over 24 again. But I'll make the theta max 8 pi. And let's see what happens there.
Hey, we have a connection.
Okay. So something I do want to take a look at is I want to go back to the y equals menu and just again look at the thing that we're plotting here. 5 times the cosine of 2 theta. And I just want to think about as theta is, if you think about our theta min, theta max, we had it running from negative 8 pi to 8 pi is what we finally settled on. As theta, when theta gets between, for example, pi over 4 and pi over 2, 2 theta will be between pi over 2 and pi. And the cosine of those angles are negative. And then we'd be trying to take the square root of a negative number. And so we're going to have, I don't want to refer to theta min and theta max as my domain, because it really isn't. It's the values that it's attempting to plot R for. But there are subintervals in that negative 8 pi to 8 pi where R is not even defined. And as we could actually see some evidence of that as we were plotting, you would notice that it would graph for a while, and then suddenly you wouldn't see any action going, and suddenly it would pick up again and start graphing some more. What it was doing was it was marching through those theta values and not getting any R value defined at all. And that's why you didn't see anything being plotted. And then it finally would get to another stretch of theta values. For example, once we get all the way to, see, I think it would be 3 pi over 4. Once we got past 3 pi over 4, we would start hitting some values that we would get defined R values again. So that's why we saw that interesting behavior. Another interesting behavior, I don't know if you'll notice, but it actually, there was a stretch. Do you see how these almost look like straight line segments near the crossings of the infinity symbol?
Sure.
These were actually close to consecutive points that were plotted. That's because this, the curve, the R values are changing really, really fast near certain theta values. And that's why we saw these kind of bizarre jumps. So it's a very interesting curve, and then we kind of picked it on purpose to illustrate some of these kind of issues in terms of thinking about the domain, especially when you're dealing with plotting on the graphing calculator. Okay. I'm going to go ahead and turn on the trace. And the trace is really neat on a graphing calculator. It's giving us, here we see the equation, our f of theta, if you will, for R. But we're given the theta value that we're at, as well as the x and y coordinates. Okay. Now I'm going to go ahead and put my theta in the middle. It's putting it in that very, let me put theta equals 0.
That's a really nice handy thing, by the way, Tom, that you can just type in.
Just type it in and it understands, okay, you're probably going to give me an independent variable value and I'll jump to that. And now if we trace, as I hit the right arrow key, it's going to be marching through values of theta, okay?
Right.
So it won't be necessarily going left to right because the theta values, it's going to be winding around. First of all, let's do a reality check. When theta is 0, the cosine of 0 is 1. So I'll get 5 times the square root of 1 is 5. So I should be at an angle of 0. I should be out 5 units away from the origin. Looks
Perfect.
good. And now as we march around, okay, that's at pi over 24. Let's do maybe 4 of these. So let's see, 4 pi over 20, that should be pi over 6. So this should be about a 30-degree angle.
Yeah.
Now it's, let's see, if I put in pi over 6 up here, 2 times that'd be pi over 3, cosine of that's a half, 5 times the square root of half. Okay.
Okay.
And it's also giving, converting to x and y coordinates so I can see what that is. Now I want to trace a little bit more. And now I'm just going to trace one more increment of pi over 24. And notice it jumped all the way to the origin with that. So this very last stretch went very quickly. That was a small value, small increment theta that got me all the way to the origin. Now I'm going to continue to march. Oh, look at this. Look what happened. I'm now in a stretch of values for theta where r is not defined. And you'll notice that my x and y coordinates are no longer defined. Okay, so there is no point on the graph for that value of theta. And I will be marching along for a while before I'm going to hit, let's see, that's, it looks like pi over 2. I still got a ways to go. I got to get to, I think 3 pi over 4 is where I'll start picking up some values again. Boom. Okay, there we are. And notice it jumped all the way out there. And now we're tracing some more of the curve. And I think I've hit another stretch of values there where I'm not getting anything defined. And finally, it picks up again. Okay, so it's kind of a, you actually have to graph over several disjoint intervals in order to generate the entire graph of this polar.
So Tom, I have a question for our people who are watching. Because this curve is drawn in kind of these disjoint pieces, how would you find the area of one of those loops?
Ah, interesting. And I think we might have asked that, Steve. And Steve, you yourself took advantage of this, and one of the other problems that you were looking at is we might want to take advantage of some symmetry.
Mm-hmm.
In this curve, I think to get one of these loops, we could just integrate from 0 to, it would be 0 to pi over 4.
Yeah, yep.
And that would get us half of a loop. And if we wanted the entire area enclosed, I could take that integral from 0 to pi over 4 and multiply it by 4 if I wanted to get all of the area enclosed by this. But making use of symmetry, I think it often comes up, especially with polar curves. And so we could even look at that. Let me go ahead and do a...
Hey, Tom.
Yes.
Yeah, go ahead and do that piece. And then I have one more question for you on maybe switching platforms really quickly. And then we're actually going to be right up against time.
Yeah.
So go ahead and finish here.
Okay. Well, I was just going to, carry out the integral. We could do that.
Yeah.
Let's go ahead and do that. So, so I'll just pull up the math menu. I see integral down there at the bottom. Yeah, FN in. I think it would be from 0 up to, let's go ahead and do to pi over 4. And I could actually pull off the R value, R1, rather than type it in again. And so I'll see our variable is theta, and we'll integrate with respect to theta, and then we'll see what happens here. And we get something that looks very, very close to 3. It's kind of interesting. Now, keep in mind, that's only half of one of those loops.
Wait a minute, we got to square that, don't we?
Oh my gosh, you're quite right.
I think we do.
Not only that, we need to take a half.
Right. Yeah.
Or you might have been thinking I was doubling already. So thank you, Steve. That was a, of course, I'm just going to pretend I did that on purpose so Steve could point this
See if
out.
I was awake. Yeah, I know.
Thank
So
you
while
for
you're typing
catching
that in-
that, Steve.
While you're typing that in, Curtis, here's another question for people to think about. You know, somebody discovered, I guess, what do we do? Graph that from -8 pi to +8 pi to get that complete curve.
Right.
It seems, just thinking out loud, it seems like there might be a smallest interval that we could use in order to get that complete curve. I have this funny feeling that that's way too big. And we ought to be able to get that curve with a smaller interval.
Yes, and I agree, Steve. I think part of what we were seeing was because it takes such a huge jump.
Yes.
I think if we had used a much smaller increment for theta, and we could have chosen some smaller intervals.
Yep.
We would need a collection of disjoint intervals to get all that we wanted.
Yeah, but that's a good exercise.
Yeah. All right. Okay, I'll stop there, Curtis. And you said something about
I did have one. Yeah, you had Nspire CAS on this, and I just thought it might be of some interest. You were making use of the trace there. Wouldn't this be a cool one to use the animated graph on the Nspire, the animated trace to do? So that same curve defined in here, I think that could be a pretty interesting one.
Now,
to see this
you guys
happen.
can help me out here. We looking at TI-Nspire now?
You are? Mm-hmm.
Okay. Well, here's that same curve.
Yeah, there you go.
Plotted on Nspire.
Yep.
And let's go ahead and try that trace and just see what happens.
Yeah, so do menu. And underneath of the menu, choose animated path plot.
Okay. I'm going to, let's see.
Oh, you're in computer view, so you need that little drop down arrow up at the top of your screen there, right at the top of the calculator screen. No.
Right there, yes.
No, over here on your software, click that little black arrow right in the center of your screen, right above Y. Click that so you can see the menu.
Right above the...
on your graph.
Yep. Right there.
Right there. Click that.
Okay.
And now there's a drop-down menu that looks like a toolbox or some tools, a hammer and a wrench.
Yes. This.
No, over here next to the paint.
Let's see. Let me go ahead and do the...
If you do calculator view, then you can use the calculator.
I think that's what I need to do is I had it in computer view. Let's do handheld. There we go.
Now just use the menu key off of the calculator.
Yeah, there we go. All right. There we go. And so we'll do a trace.
And you can do the animated graph. Well, okay, that's fine.
Oh, did I get the wrong?
Yeah.
That's okay. I was hoping to use the trace, and then underneath of that, there's animated path plot.
Nope, not 6. Try 5, Tom.
Yeah, it was. There we go. So path plot.
Yeah. Well, this is kind of a nice feature that's in here. You can actually do a polar path plot and watch that little guy jump around on the screen, which I think is kind of an interesting piece, right? So we got that, and now we'll get the remainder of that jump, and then the next one. This one is kind of an interesting one because it doesn't go how you think it would go.
Exactly.
And we just got a
point. You would think the normal way you make a figure 8 is you do that cross.
Right.
So I think that's kind of an interesting one. Notice we got the whole graph here with only 0 to 2 pi, which is, that's kind of nice. I also got a comment from one of our viewers to put in the absolute value of cosine 2 theta. Should give us an interesting one to kind of play with as well. But I think we're right at the edge of time here. So I want to be mindful of
try that. Yeah.
So I would encourage everyone to go out and try some of these curves and do some interesting explorations. There's some cool ones if you put multiple plots on at one time. There's some questions you can also ask about intersections and where the curves actually equal to each other despite their appearance, and all kinds of fun, interesting things that can be done there. Power of technology is always a good thing. So Steve, Tom, thank you a whole bunch, and thank you also to everyone who's joined us live. Continue to share these with your students. I encourage you to make use of the bulletin board blog and the assignments that Steve and Tom have written. We'll post the solutions in the coming days this week for this one, and we'll look forward to seeing you guys back here on the next time. What is that? 2 weeks from tonight?
Yep.
All right. Well, good night, guys. Thanks a whole bunch.
Thanks, Kurt.
All right. Thank you.